Hello all, and welcome to our October SERC Talk, which is the second talk of our three-part Systems and Software Qualities Trade-Space Analysis series. So Barry, over to you.
Okay, thank you. Well, we're extremely fortunate to have Bill Curtis as a speaker in this series because he has been a pioneer in software quality for many, many years, and a pioneer in analyzing software engineering for even longer years. He has been part of some major corporate initiatives in software engineering at General Electric and ITT and the Microelectronics and Computer Technology Corporation, where he did a classic study of 19 projects and found that the critical success factor in these was something called the keeper of the project vision, which has become a sort of standard success factor in software engineering. Since then, he went to the Software Engineering Institute, where he not only ran the Capability Maturity Model project, but went beyond that to lead the People Capability Maturity Model, which is again a landmark in how to improve your people management. So since then, he has joined a couple of companies that went into automated software metrics, and that's where he is currently as the Senior Vice President and Chief Scientist at Cast Software. And so I'm looking forward, Bill, to your talk. So here we go.
Okay, thank you, Barry. I'll pass that. I'm going to talk today a lot about structural quality analysis and show you some data that we've collected and what we're seeing as major factors that affect it, and some standards that we've built through the Consortium for IT Software Quality, which is a special interest group of the Object Management Group, which is an international IT standards organization, and show you some ideas about machine learning, since that's now starting to enter the software quality world and offer some strong possibilities for doing better predictive analysis of what's going to cause problems. So let's launch into this. We're in the era of 9-digit glitches. And I don't mean bits and bytes. I mean dollars and euros. Let's see the one at the top there, Knight Capital. They had a failed update that accessed some old and out-of-date trading algorithms and dead code, and Lord knows it should have been dead. And within 30 minutes, they made $440 million worth of bad trades, and they were bankrupt. And we've seen these kinds of things over and over. Target, their $200 million security breach. Equifax, and usually what happens in these is you fire the CIO, and a couple of weeks later you fire the CEO. And so we're seeing that when glitches start dealing in the 9-digit era, where they're starting to affect $100 million or more of corporate costs. That this is no longer a CIO issue. It's no longer an IT issue. This is a boardroom issue that affects the entire senior executive team. And we're starting to see senior executives way outside of IT being terminated because of glitches, because there wasn't adequate process in place for managing the risk to the business of IT systems, because more and more of the business is now being committed to IT. More of the business processes being run by computers, and therefore one of the largest risks now is risk coming from IT, and it's the senior execs that are accountable for these kinds of problems. So what they need, frankly, is better ways to evaluate the risk of their applications. And this is not just functional risk. This is really the engineering of the applications that's causing these outages. These are not that I got the functionality wrong. These are that I didn't build it according to good software engineering principles, and I had a failure due to some engineering problem in the code, not necessarily something that was functionally incorrect. The old definition of quality, the traditional definition of quality, is that it's the degree to which a product meets its specified requirements. And that's all well and good, and that's still critical, but it's simply no longer adequate. We know it's not adequate in the IT world because, number one, we know customers struggle to state what their functional requirements are, so we keep discovering those. And that was one of the major motivations behind Agile methods, is to really build these things in iteration so customers can continue to evolve what they understand their functional requirements are. But even worse, they simply don't understand what non-functional requirements are. They don't really understand what they should be asking for in terms of security or reliability or maintainability. It's just like if you're building a house. I can tell you what I want the kitchen to look like and the bedroom and the master bathroom to look like. I have no idea how to tell you how much weight the walls need to bear to keep the house upright during a storm. You're a developer. I expect you to know that. I expect builders to know those things. And that's why our customers would expect people building software to understand what the engineering requirements are, and they shouldn't have to tell us. We should know how to build reliable, trustworthy, secure, maintainable systems. In fact, Diomedes Spinellis, who I believe is still the editor of IEEE software, wrote a great book called Code Quality, and in it he said, look, the catastrophic problems we're seeing are more the result of non-functional issues than functional issues. It's these non-functional engineering issues that are causing the problem, and those are very difficult to verify. It's really hard to write test cases for these things. In fact, for reliability, you'd look more at mean time to failure over a long series of runs than to any specific test case. And in fact, if you go further into that, Barry and my late friend John Musa, who was a guru in the reliability world, said, look, you need to be able to create a base of test cases or data that will hit the system that's reflective of the population that will hit the data in actual practice. If you're just hitting it with random data and it doesn't reflect what's going to happen in real practice, you still don't know how reliable the system's going to be. So these engineering issues are challenges, and developers need tools that can help them really evaluate these non-functional properties of the system to see where they have the biggest problems and what they need to do to make the system more reliable, more secure, better performing, more maintainable, what have you. So that's what this talk is really going to address. Now, as you can see in the title here, apps are a technology stack. You know, I'll claim I'm the greatest Java developer my university ever produced, and I build beautiful, elegant code, and I'm just wonderful, right? And so I build my components, and I run them through some freeware analysis tools I got off the net, and I show that it's really elegant and beautiful, and I submit it to the build. Well, the problem now is that it's going to go into my Java code is going to fit with all the other Java code that's being built, and there's a lot out there. And this goes beyond what most of the tools can evaluate, because there's just a massive, complex body of business logic out there, and we've got to be able to evaluate how my components interact with all these others, and which interactions are going to be faithful and which interactions are going to have problems. But that's not the big problem. The big problem is that any modern application is a stack of technologies written in different languages, maybe sitting on different platforms. So I've got a user interface that's written in JSP or ASP, and the business logic is Java or .NET, and it's interacting with frameworks or through frameworks like Hibernate or Struts or Spring or what have you. There's a lot of SQL queries probably going in a database. I may or may not know the nature of the database that's being used. And if I'm in a banking application, all this is interacting with some ancient COBOL system, and it's not documented, and the guy that built it's dead. So these are challenges that no single developer can understand all the interactions in a modern business application. And if you say, yeah, well, let's go into embedded systems. Well, we find you talk to embedded systems people, and they'll tell you we're putting so much more functionality onto the chip that it's starting to look like a business application in embedded code. It may all be in C and C++, but more and more we're making what's going into embedded systems look like what was traditional in a business application, with all the different capabilities and functionalities that we're embedding in the code. So this is a challenge. In fact, no team probably understands the entire system and all the interactions. You know, in the old days, if you do Fortran or COBOL, you could pretty much understand the whole system, but that's simply no longer true. And to manage this type of complexity, we need tools. We need a lot of technology to help reduce the amount of complexity the developer has to deal with when they're thinking about how do my components interact in the layer they're in, and with technologies and other layers that it's going to have to interact with to execute the functionality of the application. So this is really the software engineering challenge of large modern business applications that represent stacks of technologies. It's even more challenging when we get into systems of systems that are interacting, and that's certainly going to be true as we enter the era of the Internet of Things, where you've got lots of different kinds of systems interacting to create different kinds of functionality. So we're in what I want to call the fourth wave in software engineering. Barry and I were there in the first wave back in the 70s, when everything was being written in assembler and nobody could read it, even the guy that wrote it sometimes. And so we realized we need higher level languages so we can actually understand what the code is doing and how it's been written, and we need structured programming to organize it in a way that makes it much more readable and understandable. And that was really up to about 1980. And then the system started getting so big that fourth generation languages and third generation languages were no longer adequate to help us manage these large complex systems. And so we created design methods like structured analysis and Michael Jackson's system design method. And we were told that if we'd only spend several $1 million on case tools, we were guaranteed an order of magnitude improvement in productivity. And this was the rage in the 1980s. And people spent millions of dollars on case tools, but by the middle to the end of the 80s, it was clear instead of an order of magnitude, it was really only a 10% gain in productivity, and that result was replicated several times. And so I was at the Microelectronics and Computer Technology Corporation, MCC, the American Fifth Generation Computer Research Operation, and we knew that if we would just build more sophisticated tools and more sophisticated languages, we'd solve the problem. Right, and a lot of the research labs around the world were doing the same thing. They were going into more sophisticated methods and tools. One guy said, "All of you folks are wrong. You're barking up the wrong tree. That's not going to solve the problem." And that person was Watts Humphrey at the SEI. And Watts launched the process wave in software engineering, the third wave, saying, look, the problem is not that the tools aren't good enough and the languages aren't good enough. They actually are. The problem is that the process is out of control. You're giving people schedules they can't meet, so they're running pell-mell crazy up and down the hall, slamming out code, working nights and weekends, making lots of mistakes, and not having time to fix them. And so Watts started the maturity framework, started developing that. He asked me to come replace him when he retired, and we took his initial framework and filled it out with what became the capability maturity model, the CMM. At about the same time, folks over in England were starting to build IDLE, which says, well, let's apply some processes to the service side of IT. You had the people in the Project Management Institute starting to build out their body of knowledge. And by the end of the 1990s, you really started seeing the Agile method that sort of work start to grow, where people were realizing finally you really do need to take this on in an iterative fashion. We need to start building systems in an iterative way because people really can't state their complete requirements up front. We need to give them something they can look at and work with and then say, okay, here's what I need next. Here's what we really want. And so Agile methods started taking off. Today, they're pretty much the common way most systems are built. And I've got some data to show you some of the issues in Agile methods in a second. But that was fine. That was the process wave. And we saw in the business the same thing was going on with Six Sigma over on the business side, where they were trying to get their business processes improved using these kinds of statistical and process analytic techniques. And they had a requirement in the Six Sigma world for the amount of benefit you would get from an improvement in order to justify taking it on. And eventually they ran out of runway. They sort of ran out of improvements they could make to get a sufficient benefit from improving their process. And that's when they started the Design for Six Sigma work, which says, the next wave of improvements has to come from improvements in the product itself or in the way we, the way we design the product. And so that was the Design for Six Sigma movement. We had the same thing happening in software engineering, in that we started seeing in the early 2000s increasing amounts of research and work on the architecture of the product itself and how we can get improvements in both quality and productivity and other things from improving the architecture. We started seeing more measurement of the structural aspects being undertaken and improvements in those measures, and a real focus. Of course, we've been focusing on reuse since the 70s, but we found that you really have to get to a level 3 environment to make that effective. You really need to have a process that people trust, and then they'll trust the things it built, and then we can reuse those. So we really started to see serious work on the product itself emerging in the 2000s, and that's the fourth wave in software engineering. And the part I'm going to talk about is how do we measure the product, not just the process, but the product itself, to know how we can improve it and get benefits from that. Here's some data actually on does improvement in the product generate benefit. This is a chart developed by a large system integrator over in Europe, and this is on about 20 data from 20 of their customers. I think there's about 21 applications that they're maintaining on behalf of the customer. They're using the tool that we developed at CAST, and it has measures for robustness, which is basically reliability, security, performance efficiency, and two aspects of maintainability, both understandability and changeability. And we can pull those together, sort of aggregate those into a total quality index, and they were using that to evaluate do overall improvements in the total structural quality of the application reduce the ticket count, tickets being operational incidents that occurred. And lo and behold, this is a log chart. Lo and behold, they found that as the total quality index got better, it's measured on a scale of 1 to 4, that the overall number of tickets went down. In essence, there was less corrective maintenance to do. And in fact, when they did their deeper analysis, they found that their regression analysis, they found that that a change of about 0.24 on this 4-point scale actually would cut maintenance effort by 50%. And so they got a tremendous benefit from continuing to make improvements in the overall total quality of these applications and cutting the incident rate in operations, which cut the corrective maintenance effort pretty dramatically. So and we've seen other charts like this from other system integrators that showed that the more structural quality improves, the less cost you have in corrective maintenance. Does this work in an Agile environment? A lot of people in Agile and DevOps environments say, look, we don't have time for all of this analysis and running all these tools and whatnot because we're on very short cycle times. Well, this is a result from Fannie Mae, which had a very effective DevOps transformation. Fannie Mae is one of the big mortgage management companies that the federal government established to fund the mortgage industry in the U.S. and take on distressed mortgages. And so they went through an Agile DevOps transformation back in about 2015. And you can see the large blue bar there over on the left side. That was the result from their waterfall. They were running traditional waterfall projects at about 18-month release cycles. And that's the number of automated function points, or the average automated function points produced over that course. And as they transitioned to an Agile environment, you can see that they're at R1.1, sort of in the middle of the chart. They were really getting used to what it meant to be agile and trying to do this in a DevOps environment. They weren't, they were starting to slowly get more added, modified, and code produced. And by the time they get to release 3, you can see it. Now they're getting the hang of it. They're actually able to work at a much more efficient pace. But if you look across their DevOps transformation here, there's about a 6-month period where they've gone through about 10 sprints. And if you add up the amount of functionality in that 6 months in terms of automated function points produced, it was far more, about 28% more than they had produced in their waterfall environment. And they found they were able to sustain that. They were getting a pretty substantial improvement in productivity in terms of the amount of work produced, but they also saw a very dramatic reduction in their critical defects per function point. And that's the yellow line there, which was about 41% fewer defects. Why? Because now as they go into an agile environment, they start testing the code much more frequently, identifying these defects much more frequently, and getting them out of the code before they release it into their operational environment. So they were showing that they're using function points as a way to measure size. They have an automated tool for doing that, and they were finding that they were showing pretty dramatic improvements in critical defects they know they had to fix. So this also means they're cutting their corrective maintenance effort, which is going to improve overall the amount of functionality they deliver per release in the future. So there's an article on this in the last January's IEEE software that goes into some depth about how they were using structural measurement to evaluate tools, what tools they wanted in their DevOps environment, what was effective, what was not effective, what processes were working better. So they had a very effective use of this kind of measurement in helping guide their DevOps transformation. So these kinds of measures do work and actually can add great value during an agile DevOps transformation and add to the overall results you're getting from a DevOps operation. This is some data we have at CAST. We've got a large repository of data we've collected from, at this point, well over 2,000 analyses of large applications. In some cases, we've got repeat analyses as they come to release it. And so every couple of years, we do an analysis of what are the major drivers of software quality, structural quality in software. And you can see there's 5 measures here: robustness, which is reliability; security; performance efficiency; changeability; and understandability. We call it transferability because it means how fast can I transfer it from one team to another team, and they understand and they can get up productive and understand what's in the code. So that's really understandability. And one of the things we found, and this is the major factor affecting structural quality in these data, is that level 1 environments are absolutely terrible. They just don't produce good structural quality. It's much better when you get into level 2 and level 3 environments. Level 1 is where most frequently you're getting schedules you really can't achieve. Somebody just makes a commitment, says, okay, get it out by Christmas. And you say, look, it's going to take till next June. They say, we don't care. We made the commitment. Get it done by Christmas. And so people are running wildly trying to crank out code as fast as they can. They don't have time to find the defects. They don't have time to fix what they find. And so they're just releasing code that they know has problems, but they've met the deadline. So this is a serious problem. It's what the CMM was designed to fix, where process problems like that. Level 2 environments, applications, different projects start getting control of their commitments, especially allowing developers the time to do professional work. And so we see a dramatic improvement, a significant improvement in the structural quality of the code when you start controlling the kinds of commitments that are made for the project. We didn't see a large increase going to level 3. It didn't seem to make an improvement. The reason is level 3 focuses on getting a common process across the organization. And the benefit there is primarily emerges from an economy of scale. We've got everybody on the same page. We typically see some pretty good productivity gains, but that's different from the kind of issues we're looking at here in terms of structural quality. But we did see that you can see the percentage of variance achieved down there. Those are pretty significant correlations and pretty significant gains from starting to get control of the kinds of commitments that are made for the development teams. And that's what it explains what I just said. Another factor we saw having a pretty significant effect was the method that was used for development, and we consistently have found that hybrid methods are superior to Agile or Waterfall, and by far the worst is having no method at all. I'm shocked if people would even admit they don't have a method, but they're willing to at times. But what we find is that people that are doing hybrid methods, DSDM or scaled Agile or some of the other methods that put an upfront focus on getting the architecture set, not necessarily getting the entire system designed in detail, but at least knowing we've got the right architecture for the kind of system we're going to build. Because we can refactor the components, but we can't refactor the architecture. Basically, it's kind of throw it out and start over. So getting the architecture right up front is fairly critical, and then you can go into the fairly rapid Agile iterations for building and testing the code that's fitting into that architecture. And we found that those that take this hybrid approach have a superior result in terms of structural quality to folks that don't. We didn't find a lot of difference between Agile and Waterfall, but both of those were across most measures superior to having no method at all. But the hybrid seemed to be the winner because it combined the evaluation of the architecture with the rapid feedback you get building code through Agile methods. So that was sort of the second. Those were the two biggest factors we saw affecting structural quality in terms of the things. We looked at age, and we looked at industry, and we looked at all kinds of factors. But the two biggest factors were the discipline applied to the process and the method that was used, especially methods that combine looking at architecture and then going into rapid Agile iterations to build the product. Now, we're starting to see machine learning and AI-type concepts more and more being explored in research environments, being explored by tool vendors as ways to improve how we're analyzing quality and how we're giving feedback about the quality of the product. And when we talk about machine learning, basically some sort of simple things. We're talking about creating and using models, learn from data about the application, learn from analyzing the application or the data that the application produces. And in many cases, it's learning without being explicitly programmed. Back when I was at MCC, the rage was rule-based systems. All the AI was rule-based. And the problem there is that's fine if you're in a very well-defined domain, tightly defined domain where you can write the rules that describe all the interactions. But that's not the real way the real world works. It's not the way software engineering works. And once you go out of those domains, rule-based systems didn't work quite so well. So we hit an AI winter back in 1988, and it certainly killed MCC, but it really kind of put a sort of slowdown on some of the work, especially with rule-based systems, because we needed something different. And people started exploring systems that work more like the brain works, neural nets and genetic algorithms and a number of other techniques. And now we're starting to see those being applied to software engineering. And as you have more data and learn more about the system, you can improve the performance of these systems in terms of providing valuable information. Number of different methods. There's a number that are just straight statistical methods where we're trying to fit a model and find out what's the best predictive model for predicting quality or maintainability or some other aspect of system performance. There's unsupervised models, that clustering techniques that start trying to explore the system and learn about it and discover some various aspects of the system and suggest various kinds of ways to evaluate the system. There's supervised learning where we're actually giving feedback to learn and categorize various things. For instance, at CAST, we're now engaged in a big project to detect false positives when we give feedback from structural analysis and categorize a result as a positive or a false positive. And then there's reinforcement techniques that really learn from what happens to the system to predict in the future. Can we predict what's going to happen by seeing various things that in the past have predicted various outcomes? Some of the use cases, defect prediction is a fairly common one, especially in academic environments where we're using regression methods or other kinds of techniques to predict which components will have the worst defect records or what's going to happen in operations. Supervised learning, especially for behavior prediction, we're using it, for instance, to predict false positives from the results of static analysis. And there's a good deal of work now, especially in some of the system integrators and big organizations, to look at discovering what components might be the best candidates for creating microservices. And there's numbers of clustering techniques and training techniques that are used to identify components of large systems which might be good candidates for being turned into microservices. So this is an analysis of these various techniques that was done by the Global Institute at McKinsey, and they looked at lots of techniques and said some of these are statistical, some are unsupervised learning, some are supervised, and some go a little bit beyond that into reinforcement. And I love the fact that they included lots of classical statistical techniques. I never really thought of these as machine learning, but I guess you can classify them that way if you're saying we're looking at the data and doing, regression analyses and other kinds of statistical techniques to learn about the system and how it performs. That's great, because that lets me say I've been doing machine learning since 1973, which is, I guess, before a lot of the graduate students that are listening in were born. And then you get into adding in unsupervised techniques, and one of the techniques there is reducing the dimensionality of the things we're using in prediction, according to the Global Institute here. And, that would be things like principal components analysis and factor analysis, and I've been doing that since 1974. So I can claim, although I don't personally believe it, that I've been doing machine learning since the early 70s. But what I really think of machine learning is more the supervised techniques where we're actually trying to train the system to learn so it can then on its own begin predicting things, or classifying things, or helping us manage the complexity of what we're dealing with large systems. And so I can't show you the results yet because I don't have permission from the customer to reveal them, but I'll tell you about some of the work we're doing. One of them is in using a classifier system that we're training to look at the results and have the organization tell us, in your mind, is that a false positive? Because they get tired of getting lots of feedback from static analysis systems and saying, most of what I'm getting here are false positives. Now, there's two kinds of things they're calling false positives. One really is a false positive. That's not really a problem. It's a pattern, but it doesn't represent a problem in reliability or maintainability or anything else. There's a second one that says, yeah, that is potentially a problem, but it's one I'd defer correcting because it's just not important to us. And both of those are often classified as false positive, but they're very different, because something that's a deferred problem may not be a problem in this system, but might be in another. For instance, there's all kinds of problems that may come up in my internal HR systems that I don't think are really worth fixing. But if that problem were to happen in one of my customer-facing retail systems, it would be a severe problem. So in some cases, we need to learn what kind of system that we're analyzing to determine whether that's a false positive or not a false positive. So again, that's part of training these things. And it means that you really need to look at the domain of the system as you're training it to determine what, does this represent Class A or Class B? And so we're finding that what we would classify in this case is a positive or false positive, would differ based on the nature of the system. Another technique we're using, and is not listed here, but is genetic algorithms. And we have some work in one of our service operations where we're working with customers to identify the optimal set of problems that are identified through static analysis that they need to fix to get a result they want to get. You can't fix everything. And sometimes if it's a million-line system, you're going to come back with thousands of problems, some of which are big problems, some of which may not be. And so the customer, the owner of the application, needs to decide what's important to me. Do I want to fix reliability issues, or do I want to improve security? Or if I'm on a contract maintaining this system, I may have an overall quality threshold that I need to achieve. And so it doesn't matter what kind of defect it is. I just want to get the maximum number of defects I can fix within the time limit and effort limits I've got to achieve that result. And so we can use genetic algorithms to run lots of simulations and select the optimal set of problems to fix to achieve the objective I'm trying to achieve, because it takes time to fix the defects. I can't fix everything, and I need to know which set based on the time it takes to fix them. I can fix within the allotted time period to get as close to the quantitative result I'm trying to get, whether it's a reliability result or a security result or an overall quality result. So again, that's a use of genetic algorithms to come up with a remediation plan that maximizes the result I'm trying to achieve when I make the fixes that we're required to make. Now, I'm going to show you a result that I can show you. It was published in the literature. It was done by Kumar and his associates over in India, and they were trying to identify change-prone components. And there's lots of techniques you can use for this. They had 21 software measures. These are classic measures, things like the object-oriented measures, McCabe cyclomatic complexity, some size measures, a number of other things. But the fact is, you wouldn't want to use 21 measures every time you're trying to predict a change-prone component. It's just too many. So they reduced that through techniques like principal components analysis, factor analysis, to come up with a reduced set. The nice thing you can say, look, lots of these measures correlate so highly, we'll just use principal components to create, organize those into a fewer set of components that will allow us this predictive capability. So there's had 5 predictive features that came out of that analysis that really reduced the 21 software measures based on the intercorrelations down to a basic set of 5 that don't correlate so highly. And if it's principal components, they don't correlate at all. And then they ran that through 21 classifier models. They had different techniques they were using for trying to predict change-prone components. And they ran this against this data set, this application, and they found that by far the best model was least square support vector machine with radial basis function as a way to adjust the results. I don't have time to explain how all of that works, but that was the technique they found best. The second best technique was a nonlinear ensemble decision tree for us. This was a specific technique for this analysis. I have seen the least square support vectors come out as very effective in other studies, so I know that this is a little bit more general result. But one of the things you have to watch for in machine learning studies when you're doing this type of study is that you need to cross-validate the result. In many cases, you've taken advantage of chance variation or of variation that's specific to that application or that set of applications caused by factors that may not be causal in other data sets. So these things need to be cross-validated if they're going to be used effectively in industry. Now, one of the reasons for doing machine learning and publishing these papers so you get to get them accepted at conferences, so you can travel to really neat places around the world to present the paper. And you might also get tenure as a result of it, and that's great. But for us to use this in industry, we really need these things to be cross-validated. To get it accepted at the conference, it doesn't necessarily have to be cross-validated. But we do need to know that if we're going to be applying this across a large base of applications, that we know that the model that's been selected and been developed is relevant to most of the applications, or we need to know what its limitations are. It's relevant to this class of applications, but not that class of applications. We need a different model. So cross-validation becomes fairly important because we do see differences across different types of applications and in terms of what seems to be the best predictors. And one of the questions you really have to ask is, okay, we have this nice model we developed through machine learning. Is it better than a simple code complexity metric in this case? Are there simpler solutions that give us almost the same amount of predictability or close? It's sort of the old Occam's razor. The simplest explanation is typically the best one. And so that would be a question you need to ask. Is this predictor significantly better than just one or two simple code complexity metrics or whatever metrics are available? And that is a critical factor to demonstrate. But we may find that if we expand our thought process a little bit, we can find other factors to add into these predictive models that occur before we've got the code that tell us what's going to happen when we produce the code. Things like some of the process issues I showed you earlier, the nature of the method being used. Actually, I've always found by far the most predictive factor in terms of the change proneness or the quality of a component is on the front cover of Barry Bean's book. What is it? Right? The biggest single factor I typically find is who programmed it. Right? The individual differences among developers are absolutely enormous. And the things they understand about the application, about the language, about the kind of technology they're using differ widely, and that has a tremendous impact on the quality of the resulting components that are being built. So that might be one thing that you look at. Who built it? Programmers don't necessarily like to be evaluated in that way. But if you use this kind of feedback as a way to help people learn where they're making their mistakes, and it's really a learning mechanism, then there's not so much resistance. It actually becomes beneficial, and people actually appreciate the feedback because they can learn much more rapidly what kinds of things they need to correct in their development activities to get the best result in the components that they're building and integrating into a larger system. So in the remaining few minutes, I want to talk a bit about what we're doing to create standards for these kinds of structural quality measures. Back about 2009, people were going to, especially system integrators and outsourcers, were going to OMG, the Object Management Group, which is the International Standards Organization for the IT world, and some to the SEI, to the measurement folks at the SEI, and say, look, we're seeing these measures for reliability and security and maintainability and whatnot being included in our contracts as the equivalent of a service level agreement that we have to achieve, but there's no standards. Every customer has a different definition of what they mean by security or maintainability, and we can't deal with 75 different definitions of these things across all our contracts. We need standards. Could you develop those? So Paul Nielsen, who heads SEI, and Richard Soley, who heads OMG, got together and said, let's create a consortium to create these standards. We can make it a special interest group managed by OMG. Originally, when we formed it in 2010, we had 24 companies join for a modest fee. We've since changed to a sponsorship model where, in this case, 7 companies are providing the funds to manage the website, to sponsor our conferences and our various standards activities. But CISQ was chartered to actually come up with automatable measures, specification for automatable measures of size and structural quality that you can measure from the source code. So that's the critical issue here. It's automatable. You can measure the source code and develop these measures from it. So we held executive forums in Washington, D.C., in Frankfurt, Germany, and in Bangalore, India, and got executives together and said, if we undertook this consortium, what measures would you want us to start with? And they came up with 5 measures. We went through a voting process, and they said, look, we need a size measure for function points. We're absolutely fed up with the cost of manually counted function points and the fact that different function point counters will come up with different counts on the same piece of code. We need something. We need to automate this to reduce the cost and increase the consistency. Make it similar to IFPUG, the International Function Point Users Groups counting guidelines, but automated. And then there's 4 structural quality measures: reliability, performance efficiency, security, and maintainability. So we worked for a couple of years and produced those standards through OMG. OMG has a much more efficient standards development process than ISO, which is why I chose to go through OMG. And so those are now approved standards of OMG. We're starting to move those through to the fast track. OMG has a fast track over to ISO, and we're starting to deploy them through workshops. I'll tell you a little bit more about that in a later slide. And now we're starting to work on newer measures. We're right now engaged in updating the structural quality measures to deal with embedded systems. And the initial ones were primarily for IT systems, business systems. But actually, as we do this, the embedded gurus we've got working on us are telling us there's so much functionality now being put on the chips. It really is more and more embedded systems are becoming more and more like IT systems. There are a few issues with real time that are different, but the fact is these are more and more acting like classic IT systems, everything being moved onto the chip. This is how we built these structural quality measures. We identified weaknesses that people felt had to be remediated. They had to be fixed. There's hundreds of weaknesses in each of these areas, and we didn't want these measures to reflect that, because if you can defer it forever, it's not critical. So we really went down and picked weaknesses that people felt you need to fix that. There needs to be a plan for getting that out of the system. For security, the work was largely already done. That community, the Common Weakness Enumeration community, that repository has over 800 weaknesses that hackers exploit to break into systems. But they've decided on what are probably the top 25, the 25 that are most frequently exploited to break into systems. So we just accepted that as the measure. There's 22 that you can automate that can be detected through static analysis. And you can see here the SQL injection, cross-site scripting, buffer overflows. Those are the big 3. And the embarrassing thing is SQL injection is still one of the top ways that hackers break into systems. It's embarrassing because we've known about SQL injection since the late 1990s, and yet we still find those problems inside systems. And in fact, when executives try to explain what happened, there was a SQL injection attack on a British telecom company called TalkTalk, and the poor lady that was CEO created a YouTube video where she tried to explain what happened and apologize for it because all their customers' data was exposed. And she said, we had an injection problem. It sounded like kind of a drug problem. She simply had no clue what SQL injection meant. Maybe we're injecting SQL into SQL addicts or something. But the fact is, executives don't understand this stuff. They need to rely on us to use these kinds of metrics to identify the most significant problems and identify a remediation plan to get them out of the code. It also allows us to measure technical debt. Technical debt is becoming an increasingly popular concept. And we've estimated, we had the professional developer estimate the effort to fix these problems. We can sum those across the instances of each weakness in an application. We can apply some adjustment factors based on the complexity of the component, how connected it is to the rest of the system to adjust the effort. And then we can sum those up for all the weaknesses in these 4 different measures, reliability, security, and whatnot, to determine the technical debt related to things like security or performance. We can sum those up to get an overall technical debt measure, and that correlates with the corrective maintenance effort that you're going to face in the future, which is what executives want, is tell me what it's going to cost me to fix the things we've got to fix. Not everything, but the things we need to fix. And it's a predictor of the overall cost and effort to do this. This is not a perfect measure, but at least it's a good correlate. It's not exactly the way that Ward Cunningham talked about technical debt in his original concept back in 1992. He was talking about, decisions we make that are suboptimal, but we want to go ahead and get the code out. Well, we're talking here about all kinds of problems in the code, whether it was a decision you made or not, because that's what CIOs want. They want a way to estimate what is all this technical debt in my system going to cost me to fix, and which applications are in worse shape than others. So this at least is one version of technical debt, not the only version, but one that can be used to estimate cost and effort for different applications. We've done our best to keep this consistent with the overall ISO quality model in ISO 25010, which defines 8 areas of quality. You can see the ones that are in blue there are the ones that we have automated. We've tried to keep very close to those definitions. We've looked at the sub-characteristics to make sure we've covered the domain. The problem is ISO, the actual measures are defined in ISO 25023, and they do not get to the source code level. I'm the American rep on that committee, and I've been trying to get them to that level, but I've failed miserably. So the truth of the matter is the CISQ measures actually supplement the ISO standards by providing measures that you can actually assess of structural quality down at the level of the source code. And so we're making some improvements in the overall quality model now, and we're going to get them to reference these kinds of measures, these structural quality measures, at the source code level in some of the future revisions of 25023. Look, I said earlier at the very beginning, executives are on the hook for what's happening. When we have these 9-digit glitches, these $100 million, 100 million euro plus outages or security breaches or problems, the fact is it's the executives that are being interviewed by the press, by the Wall Street Journal or the London Times. And they need a way to protect the business. And it's no longer adequate to say IT is doing what it can. Or the executives need to say, if they're going to execute their governance, this is what I expect you to achieve in order to reduce the risk to which we're exposing the business. Because I owe that to the board of directors and the shareholders. Or if I'm a government agency, I owe that to the citizens of my country that we're trying to do the best job of protecting their private information and delivering the service that we're supposed to deliver. So we are going to release a Trustworthy Systems Manifesto on the 16th of October at the Cyber Resilience Summit that CISQ is hosting there in Washington, D.C. We hold 2 of these a year. We've also held one in Europe. I'm going to hold one in India in November. But we're going to release this Trustworthy Systems Manifesto as a way for executives to say, this is what I expect. I don't care what methods or processes you use, but I expect you to apply engineering discipline to them. Using Agile methods is not an excuse for hacking. It requires discipline to do it properly, and I expect you to apply the proper discipline. I expect we need to identify the tolerance we can have, the risk tolerance we can have for different systems, and I expect you then to perform the quality operations you need to perform to make sure we can achieve those tolerance thresholds. For instance, in a telecommunications system, I can allow a certain amount of downtime. I'm not going to pay you to go beyond that, but I need to know you can achieve that tolerance. We can tolerate maybe 5 minutes per time period, whatever the time period is, but we can't tolerate beyond that. So express those levels and have the quality assurance methods in place to achieve them. I need to know what the provenance is of the system components. There's license issues, but even worse, if there are known vulnerabilities to some of the open source components you've included, we need to know that. That's what happened to Equifax. There was a vulnerability that was exploited by a hacker that was already published, and they hadn't fixed it. So we need to really understand the provenance of all the components in our systems so we can protect ourselves from license problems, from hacker problems, and what have you. We need to proactively defend the system and its data. Bobby Stifley, before she took over the CERC program at the SEI, was running a lot of the cyber resilience programs at Department of Homeland Security, and she was on a panel where several years ago where she said, look, the only safe assumption you can make is that the hackers have already penetrated your system. They're already inside. The question you now have to ask is, how can I protect my data? How can I protect the confidential information inside the system from them getting it and exposing it to the world? So we need to proactively defend not only the system, but the data inside the system, assuming that they may have already penetrated. And finally, obviously, we want resilient and safe operations. So this is really designed for people in positions of responsibility to say, this is what we expect. It goes beyond the Agile Manifesto, because that doesn't so much say what we want as a result of doing the work. That just talks about the process of doing the work. We really need to talk about what we expect. Trustworthy is the word that is now emerging. There's a trustworthy charter in Europe trying to get governments to look at what they need to do to provide trustworthy systems for their country, and the same thing here. This is an objective to create a manifesto that says some of the things we expect an organization and developers to do, and the system to achieve to be trustworthy for the users. So I invite you to join CISQ. Membership is free because we have sponsors. You can see the member button there below the nice lady, and you just push the button. We'll ask you some questions. We'll send you a password, and you're a member. We have the standards inside here. We have some white papers on how to use them in service level agreements and contracts. We have the presentations from all the previous cyber resilience summits on various aspects of cyber resilience. So there's a lot of things here, and membership is free. We have several thousand members now from government agencies, from corporations, from universities, and I encourage you to join. So let me end the talk here, and we can turn it over to Barry, who I think wants to say something about upcoming events and maybe allow some questions.
Sure. Mimi, were you going to cover the upcoming events? Or? Oh, okay.
Sure.
I guess I'm going to do it. Yeah. So yeah, this is the second out of 3 of these presentations that we're having on qualities. The one that comes next is in December 11th. Xavier Franch is the speaker. He is the leader of the leading European consortium that is addressing software and systems quality, which is called Rapid Quality, and so they're trying to do both quality and speed, and so again we'll look forward to his talk, and it will be the second Wednesday, because he had something else on the first Wednesday, but December 11th, same time, 1 p.m. Eastern, a.m. Western. So there are some other things that the System Engineering Research Center is sponsoring. One is we have a sponsor research review. SERC is sponsors are the Department of Defense, and so every year we owe them a summary of what we've done in research from the last year. And another thing that we do the previous year day is to choose the top doctoral students that have been working on the CERC projects, and then give them a chance to present what they've been doing. So again, this is something that there's a nominal fee for industry, but it's free for academia and government. Mimi, do you have anything else to say about where people can find the charts for this and on the CERC website?
I think you have it pretty much covered, Barry. It's right on the SERC website. If you go up to the events section, you'll be able to find the information on SERC Talks as well as the SSRR and right on the homepage. And thanks again, Bill. We'll be sure to include the information about the Cyber Resilience Summit. I'll have to tag up you to get that information on the SERC website as well.
Okay,
great.
Good. Do we have some questions for Bill?
I don't actually see any in the chat or the Q&A.
So if some come in, I'll be happy to, email them to me. I'll be happy to shoot back answers.
Perfect. And you have your email that'll be available on the SERC website. By Friday, we should have the SERC Talk up on YouTube, and we generally get some input afterwards as well. We'll direct them your way.
So you can get them. Yeah, you can get me at curtis@acm.org.
Perfect.
That'll be good till a year after I'm dead, because it'll take an extra year for ACM to figure out a different.
Okay, well, we'll wish you good luck with all of your health problems, and so thank you very much. It's been a super informative approach, and it's good to see that it's focused on the people who are making the big decisions in major organizations and what they're trying to do and how you're helping them do all of this by getting better handles on evaluating the quality of what they're rebuilding and evolving. So,
thank you.
Okay, so thanks for everything, and Bill, I'll see you in a couple of weeks.
Yeah.
At the summit. Yeah.
Look forward to it.
Okay. Thanks, everybody.
Bye-bye.
Bye.
Thanks. Bye.